Hello and welcome everyone, this is Mr. UMath again, and in today's lecture we want to have a look at the very famous series 1 plus 2 plus 3 plus 4 and so forth. So actually what you are doing is you are adding up all the integer values, and this is actually a reaction video to a video from Numberphile in which they told or suggested that the result of this summation was minus 1 over 12. Now actually sometimes in some books people tend to write this down in this manner, but actually this is not true, and I will try to explain you why this is not true. Okay, and somehow I will try to give you an insight why one could say that this sum could have such a value of minus 1 over 12. Okay, so let's just start. Okay, now what I want you to teach in this video, or better to explain you, is that we have two kind of expressions. Okay, we have one which is 1 plus 2 plus 3 plus 4 and so forth. You are adding up all the integer values. This guy is not equal to minus 1 over 12, but I will teach you, or better I will try to explain you why one could think that this is equal to minus 1 over 12. Okay, but why we know that this is not equal to minus 1 over 12 is that if you are adding up all the integer values until a number n, then you can find a closed formula which is n multiplied with n plus 1 over 2. For example, if you are adding up all the integer numbers until 10, then you have to multiply 10 with 11 and then divide by 2, and you are getting the result. Actually what you are seeing here is if you are plugging in infinitely large values for n, this guy will diverge, which is a pretty intuitive thing. If you were looking at the sum, no one would ever try to say that this has a negative value. This would sound stupid. Okay, and in this video I will explain you why one could think, or better assign a value to this, while this makes actually no sense in the mathematical sense. Now, but what is true? So what I told you was that this guy adding up all the integer values is not equal to minus 1 over 12, but what is true that a special function which is called the Zeta function has a value of minus 1 over 12 if you plug in minus 1. Okay, now where is the idea, or better the link between the Zeta function and this strange looking sum of 1 plus 2 plus 3 and so forth? They are very strongly related, which I will cover after a few slides. Okay, but first I want you to have a look at the sine function and the idea, or better the concept of a function and the representation of a function. Many times when we talk about any function, about the sine function, about polynomials or anything else, we are always having a very specific idea how to calculate this function. And this is a little bit confusing if you go up to higher mathematics. Then this kind of thinking is obsolete. So you have to stop thinking in this way. You have to have a more general understanding of functions. And now the function we want to look at specifically is the sine function. Not because it is a very special function, it's only because it has a lot of many representations that are quite popular, and many people know them. Okay, so there are not, I hope many of you guys have heard about these kind of representations. And we will start off with the most fuzziest kind of representation of the sine function. This is writing down the sine function as just simply sine of z is equal to f of z. While this is pretty fuzzy, I think this is maybe the best kind of thinking about the sine function. So it's just the sine function. Now in school you learned that the sine function, or better the value of the sine function, could be calculated if you take a unit circle and then in the unit circle take any angle alpha, and then take the intersection of the circle. The unit circle means that it has a radius of 1. This intersection between a special angle and this circle is a point, and in this point you can take its height in the coordinate system, and this is nothing else but the sine function, or better, the value of the sine function for a specific angle or a arc length. Now, as you see, this is a pretty fishy kind of representation. So mathematics and mathematicians always try to find a better kind of representation of the sine function. And here is a kind of representation which is more complicated but more robust than the previous one. It writes down the sine function, so I won't write down sine function, I will just write function is equal to a difference between two exponentials. The one exponential is e to the iz, and then you subtract e to the minus iz over 2I. Okay, now what is this I? This I is a complex number, and actually it's the unit of the complex numbers. It's called I, just simply I, and if you take I to the square, you get out -1. Okay, you might get crazy about this, but this is how mathematics works. You just try to think in other patterns. I know you heard in school I, or any number that you square, is always positive or equal to 0, but now let's think of a number I that you square, you get just -1. Okay, why not? Now this is a representation which is more robust because everyone can easily imagine something out of an exponential. If you take 2 to some power, or e to the 2, that means e multiplied with e to the 3 means e multiplied with e, and again multiplied with e. So it seems to be more understandable. Please don't ask me why this is true. I will actually do a lot of videos about this, but now just take it as given. Okay, we know that the sine function can be written in such a way. If you are even more advanced in mathematics and you know something about infinite sums and so forth, and you heard about convergence and so forth, then you can write down another representation, which is this one. You can write down the sine function as a Taylor series. Okay, and the Taylor series of the sine function is z minus z cubed over z factorial plus z to the 5 over 5 factorial minus z to the 7 over 7 factorial, and so forth. You are just having alternating terms in the series. You see that their powers is always odd, so actually z to the 1, z to the 3, z to the 5, z to the 7, and then you are dividing this with odd factorials. Actually under the z you could write 1 factorial and so forth, and 3 factorial and so forth. Now this is a more advanced representation, and it's even easier than the exponential representation because we are only using powers of z. The only thing that is confusing is that it's infinitely long, and actually calculators are working in such a manner that they are taking the Taylor series until a very specific term and then cut off, because the precision is high enough, and if you want infinite precision, then you need infinite terms. Now, this is not all. There is also another representation, which is the product representation of the sine function, and actually you can write it down as z multiplied with 1 minus z squared over pi squared, and then take n to the square, which n is a integer number. You can plug, not integer number but natural number, so you can plug in 1, 2, 4 and 3, 4 and so forth, and then you get infinitely many products. So 1 minus z squared over pi squared, if you plug in n, 1, n equals 1. If you plug in n equals 2, you get 1 minus z squared over pi squared multiplied with 4, and so forth. At first glance this looks pretty strange, but if you know a little bit about functions, about the zeros of a function, then you know that if you know all the zeros of a function, then you can write it down as a kind of linear factors, as a factorization of linear factors, which is pretty much the same which is done here in a more complicated fashion, because the sine function has infinitely many zeros. It makes it a little bit harder, but it's actually the same, because if you look at it, if you plug in z equals pi, then you get 0. If you plug in pi squared, you get 0 in the second term for plugging n equals 2, and so forth. So you can get all the zeros of these functions with this product. Now, one could think of even other representations, and there are a lot of representations. I don't know, there are so many representations of the sine functions which are not looking like the ones that I wrote down here, and this brings us to the conclusion of this slide. There is always a concept of a function, what we think about a function should do, and then there is some kind of representation which we use for calculating, for finding special properties of this function and so forth. But what you should also see here is, which is very important, is that all these representations that I wrote down are valid for every z that you plug in. Okay, it doesn't matter what z you plug in, you always get the real value of a sine function. This is not always true for any functions. You could find representations for the sine functions which are not true for every value of z. Okay, you could also find representations of other functions which are not valid for every kind of z. Okay, and this brings you to the level of the representation of the function. So we have a concept of a function, and then we find a representations, and you see there is only one functions, but there are many representations, and all of these representations have different kind of properties. They have powerful things that you can do with them, and sometimes they are just aesthetically appealing to you. Okay, let's get back to the problem where we started, and before we can actually solve this problem, we have to have a look at the zeta function. Okay, this strange wiggly sign is the zeta function, or better zeta, and then we plug in some value of s, and the zeta function was first defined by Leonhard Euler, and then was even more studied by Bernhard Riemann, who did the most important, or better, one of the most important conjunctures and modern mathematics. He just conjunctured something about its zeros, and it's a very famous problem called the Riemann hypothesis, and if you find its solution, or you can prove something, then you will actually gain $1 million. Okay, so you can get a lot of money with this. Now, what is the zeta function, or better, how was it first defined? Euler defined it as a sum of reciprocal powers of integer, not integer, of natural numbers. So for example, you are taking 1 over 1 to the s plus 1 to the 2 to the s, and so forth. And which is important about this function, it is that it is only valid, what means in the mathematical sense, it only converges, has a very specific value, if the real value of this s variable is greater than 1. What does real mean? Never mind if you never heard about complex numbers, just think about it. You are not allowed to plug in negative numbers, or even 1 would not be allowed. Now let's just write down this function without using the sum sign. It's 1 plus 1 to the 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus, and so forth. So you are adding up all the natural numbers as inverse powers. Okay, you take their inverse and take their power to the s. Now, one could dare and say, okay, this kind of condition above there, I don't mind. Just plug in -1 and see what happens. Okay, if we plug in -1, we will get 1 plus 1 over 2 to the -1 plus 1 over 3 to the -1 plus 1 over 4 to the -1 and so forth. Now what does this to the -1 mean? It means that you are taking the inverse of the number. For example, the first strange looking term, 1 over 2 to the -1, would be 1 over 1 over 2. The second term, which is looking, or better, the third term in the series, would be 1 over 3, which will just give you 3. Then you have 1 over 4, which you get 4. So actually, if you're adding up these numbers, you will get 1 plus 2 plus 3 plus 4 plus 5 and so forth. But actually we know this is not allowed because our real value of s was greater than 1. Okay, we are not allowed to plug in -1. Hence, this kind of writing down the sum as zeta of -1 is actually not allowed. And this is the error that was done in a Numberphile's video. They said that this was equal to each other, and this is absolutely not the case. Now let's have a look at another representation, and this is not the second representation you would normally hear about the zeta function. The second representation is always the Euler product representation. If you're interested in this function, please have a look at my playlist about the zeta function. There is a lot about it. You will hear all kind of representations, and I think this could be a good source for you to start off thinking, or better, studying the zeta function. Now let's have a look at the second representation, which is due to Riemann, and why this is a better representation. Better, we will see soon, is that it is complicated. Okay, now this is not the case, or better, the reason why this is the better representation, but it's obviously more complicated than the other. But the interesting part is it doesn't use infinite sums, at least not explicitly, while we have two kind of strange things here. First of all, this gamma function here and this zeta function here, which are both using some kind of infinitely expressions. But you have 2 to the s, pi to the s minus 1, you have sine, okay, we talked about the sine function, pi s over 2, you have gamma of 1 minus s, and you have zeta of 1 minus s. Now what can we do with this kind of representation? And what is the advantage of this? You can plug in all values, okay, except two specific values, 0 and 1. But this is not important because we wanted to plug in -1. This would not be a problem. Now we can use this representation to find the value of this function, the zeta function, because this above representation failed. Now we are using this representation, which is true for all values except 0 and 1. Now if we plug in -1, we get a lot of minus signs. So we get 2 to the -1, we get pi to the -1, -1, we get sine minus pi half. You see, it's pretty long. You get gamma of 1 minus -1, and you get zeta of 1 minus -1. Now let's simplify this a little bit, which is pretty fast. We get 2 to the -1, we get pi to the -2 because we had two -1s over here. We get the sine of minus pi half will give you a value of -1, and we get gamma of 2 because minus and minus will cancel, so we get 1 plus 1, which is gamma of 2, and then we get 1 plus 1, which will give us a zeta of 2. Okay, this looks nice, but we have to think about these both functions, and we will do short. Okay, so first of all, we found out that the zeta function I would say it could be written as 1 plus 2 plus 3 plus 4 and so forth, but we learned that this is not the actual value of the zeta function in -1, and we knew that actually this right hand side is not equal to the left hand side because it's not a valid representation. So we have to negate this equal sign. So gamma, or zeta of -1 is not equal to the sum of all the integer values. But what we know is that zeta of -1 is equal to 2 to the -1 pi to the -2 minus 1 multiplied with gamma to zeta of 2. Now what is gamma of 2 and what is zeta of 2? These are, the first one is pretty easy actually, the second one is pretty hard to show, but if I write it down you know what it is. So first start off with gamma of 2. The gamma function for natural numbers is nothing else than the factorial. If you don't know what the factorial is, then the factorial is multiplying all values. For example, if you take the factorial of 5, then this means multiplying 1 with 2, with 3, with 5, with 4, and then with 5. Okay, you are multiplying all the natural numbers until you arrive at 5. Then, for example, factorial of 10 is the same, but you are multiplying until 10. Now, gamma of 2, or better, gamma of n, is always the factorial of n minus 1. For example, if you are taking gamma of 10, then this is equal to the factorial of 9. So gamma of 2 is obviously the factorial of 2 minus 1, which is the factorial of 1. But if you are multiplying all natural numbers until 1, what do you get? 1, because you only have the 1. Now the right hand side problem is the zeta function for the value of 2. 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared and so forth. And the important part is that 2 is a valid value, so this representation is valid. And Leonhard Euler, a very famous mathematician, found this out, that this sum is equal to pi squared over 6. And if you want to know how we found this out, please watch my videos about the zeta function, about the gamma function. I really explain this in a lot of detail. It's not that hard, but you should be prepared to have a lot of mathematical fun. Now if we plug in these values into the upper equation, this equation, then we get zeta of -1 is equal to 2 to the -1 pi to the -2 minus 1 multiplied with 1, because gamma of 2 was equal to 1, and zeta of 2 was equal to pi squared over 6. And now magically this pi squared and this pi to the -2 will cancel. We get a minus sign in front of our value, and we get 1/2 multiplied with 1 over 6, which will give you 1 over 12. And magically now we arrive at our final step. We found out that zeta of -1 was equal to minus 1 over 12, and we know that zeta of -1 is not equal to the sum, but one could be tempted to say that adding up all the integer values from 1 to infinity will give you minus 1 over 12, and this is what was used in Numberphile's video. I'm pretty much sure that this is not that they actually know that is not true, but they wanted to make it more special and to make it look more magical, because it is absolutely non-intuitive to say something like this. And now what you should know is that this is actually not true, that minus 1 over 12 is not equal to 1 plus 2 plus 3 plus 4 and so forth. This is not a true kind of a result. So what you should have learned here is be always careful about using the term function and its representation. They are not the same. You can have a function and a representation, but the representation doesn't hold for all values. Okay, so that's actually it. I hope you had a lot of fun watching this video, and I hope this gave you a little bit more insights into some confusions in mathematics, and I hope you like my videos and you give thumbs up. If you have questions about this video or anything else, just feel free to ask in the comment section. And if you like my videos, like always, please subscribe and stay tuned, because there are many more cool videos coming up soon. So see you guys.